All right, good afternoon. It seems that we don't have as many students as we used to have, but hopefully they'll join us. My name is, you all know, Ali Kujuri. I say it because Scott is taping us. And I'm one of the organizers of this lecture series. In fact, Ronnie and Sharam also are the main contributors to this series. I would like to thank Keysight Technologies for sponsoring this lecture series since the start in 2006. And also, let me just mention that we don't have yet, I have not still gotten a speaker for next time, because we start usually the work in summer to go and find good speakers. If you know of a good speaker in the area of that you like, electrical engineering, please let me know and we can consider it, no doubt about it. Ronnie has in fact ordered pizza. It's going to arrive at 5:30, and I've had asked her to stay so that she would also enjoy eating it for the first time. Our speaker for today is Dr. Sara Kassis, and the title of her talk is Material Characterization Techniques using the Keck Microanalysis Laboratory. Dr. Kassis received her PhD in condensed matter physics from Kent University. By the way, Kent, as you know, is in Ohio, and I was looking it up at Google, and they have something like 30,000 students. And believe it or not, Kent University, I don't know whether she knows that or not, it established in 1805. How about that? Yeah, we are talking about now 210 years ago. It's good. Okay, now whether she was the first graduate or not, that's another question. Okay. Her experience includes 10 years of teaching physics and engineering in various universities. Her research interests include materials engineering and characterization, nanomaterials, and low temperature physics. So here is Sara.
Thank you very much, Ali, for that introduction. And thank you to all of you for coming. My apologies about last week. I really wasn't feeling well, and I would not have been able to do the talk, but thank you all for coming today. So today I want to talk to you about the Keck Laboratory. I know some of you had already attended the talk given by Dr. Saeed Rahimi, and who gave an overview and a history of the lab. And also, there was a little field trip over next door. Actually, it's right through that window. And many of you were able to see the tools being utilized and see where all of them are positioned in the laboratory. So for me, I really enjoy material characterization. So as Ali said, I did do a degree in condensed matter physics. So my degree also, I did a lot of material science too, because I created a lot of my samples. And so I was able to characterize them, and so I was able to utilize a lot of the tools in the laboratory that we had. So we do have a very lovely, am I turning on? Thank you. We do have a wonderful set of tools here, and it's a great opportunity for all of you as students to take advantage of that if it's interesting to you. And I see a lot of my former students and some of my current students, so hello everybody. Anyways, so I just wanted to say that you might have heard condensed matter physics. What does that mean? Well, it's an umbrella for very many topics of physics, and it includes solid state physics, which I'm sure a lot of you are familiar with, and you should be familiar with since you're electrical engineers. But it also includes so material science and engineering and solid state physics are very, very much connected, especially when using material characterization tools. So material science and engineering actually apply condensed matter physics and solid state physics. So those are the applications for the theory or the fundamentals that are developed. But all these disciplines use material characterization, but of course each one has a different reason or a different application. So they are very well connected when coming to material characterization. So I'm going to give you an overview of what the talk is about today. So I'm going to give you a background about fundamentals. We're going to talk a little bit about materials, a little bit about what is characterization, and then I'm going to talk about all the tools in the Keck laboratory, what's available, how do they work, and applications for utilizing them, and then reasons to use material characterization. So I know all of you have seen this in elementary chemistry and some class that you've taken. But the basis of material characterization is that you really need to understand elements. Okay. So the purest form of a material is a chemical element, and each of the materials are distinguished by their atomic number, and they all have unique properties. And so all the elements are actually ordered by their atomic number in the periodic table. So if you go across on the periodic table, the atomic number increases, and of course that makes each element very distinguishable from the other. Product designers, engineers, or manufacturers, they're really not interested in elements in their pure form. There's nothing really to do, there's not much to do with that. So the majority of materials are traded and processed either as an alloy, as a compound, or a mixture. So you have to do something with that element. And another fundamental thing that we need to know when we talk about material characterization is that you really need to understand how electronic structure works inside of a material. So we start with electrons and protons and neutrons, but electrons are what we're really interested in when looking at the electronic structure. So if we take a look here, we have a nuclei of an atom, and then we have surrounding shells where all the electrons are sitting. And so the electrons will orbit around the nucleus at specific energy levels, or what we call electronic shells. So each shell is denoted by a letter of the alphabet, so K, L, M, and N. And of course, if you go higher, there's more. But the K, for example, would be the innermost shell. L would be one out of that, and so on. And they're labeled, they're numbered, from 1, 2, 3, and 4. And so for each of these shells, we have what's called electronic subshells. And so the subshell lets you know further how many electrons is able to stay within that state. And so within each of these shells, the subshells can be S, P, D, and F, which are denoted by the orbital number L0, 1, and 2. And so the number of orbitals are actually there, or the number of positions, depend upon which subshell you're in. So S is equal to 1, P is 3, D is 5, F is 7. And so since electrons have a charge or a spin, let's say, of 1/2, so there's two actual states, and so the number of electrons that are possible to be in each state, for example, would be 2. So here, for example, is the 1s state. We have an electron pointing up, an electron pointing down, and their spins have to differ. And of course, there's more to this. There's more details to this that I'm not really going over, because the idea of this is that I really just wanted to bring up to you that when we have a specific amount of electrons, like let's take nickel, for example. So the atomic number of nickel is 28. And so if we take a look all the way on the right, and different periodic charts will have different of course, different areas of where to put all these numbers. But what it's trying to tell us here is that each of these numbers here, I don't know if you guys in the back can see this. Okay, good. So the very first one tells me how many electrons are in the K band, how many are in the L, M, and N. And so we correspond those bands here. So if we take a look at the electronic configuration, this is K, L, M, and this is N. And so, and here, of course, are the subshells. Here are the S's, P, and then D. Well, nickel, when you put all of our electrons in here, so one is spin up, one is spin down, and you fill them across, the way you're supposed to fill in the orbitals here is that you're supposed to have, let's say, spin up. So you fill all of them spin up first, and if there's any leftover electrons, you put them spin down going across to make these pairs. However, sometimes you see where you have two spin ups but no spin downs. So these are what we call unpaired electrons. And so the way you know what this is because in the D shell, there are 1, 2, 3, 4, 5 orbitals, just like right here. And since I have 2 electrons per orbital, in order for me to fill this up, I would need 10 electrons. Okay, but here with nickel, here is the electronic configuration of how this is written. You might remember this from chemistry. And the 3D orbital, there's only 8 electrons in there. So 2 of these electrons are unpaired. So what does it mean when electrons are unpaired? What are these called? What kind of electrons are these?
Valence.
What's that?
Valence.
Valence electrons? What's the other one?
Is another word?
Well, these are in the valence region, but these guys are considered to be conduction electrons because they are free to move around and go wherever they please. And so anytime in the electronic structure we have unpaired electrons, they will be in the valence state, but they're the topmost ones in the valence state. And so if they choose to, if they end up if they are free to move around if they like, and that's what makes them conduction electrons. And so any material that is conductive, you will find that their electronic structure has unpaired electrons in there. Okay, and so we exploit this fact. A lot of these tools exploits this fact, and so you're able to identify materials. You're able to use techniques to exploit this to take a look at conductivity or resistivity. That's for electrical measurements or for other types of reasons as well. So the fundamentals today is really just a general overview, and it's just for stuff that I'm going to, just things that I'm going to be talking about with regards to the techniques. So the electronic structure of an atom determines what type of material it is, whether or not it's an insulator, it's a conductor, or it's a semiconductor. So for electrical engineers, knowing what materials are semiconductors, for example, is pretty important, right? How do you create that, or what makes a semiconductor the way it is? Well, so Jose mentioned the valence bands. So if we take a look at these 3 scenarios, this vertical axis here gives us the energy of electrons. And so we take a look at the energy of electrons compared to 2 states. So this is actually called band theory. And so it's saying that we have a lower energy state called the valence band, and then a higher energy state called the conduction band. And when there's a huge separation between those two, it's very difficult for any electrons in the valence band, of course, to move across to the other side to make them conductive. And so this region, this space that we actually call this the band gap width. And so this is a high energy gap between these two, and it's an insulator at normal temperatures. So an insulator would have an energy band gap that looks like this. If we take a look at, so I'm going to go over to the other side to conduction electrons. And so conduction electrons, we actually have the valence band overlapping with the conduction band. And so the valence electrons, which you mentioned, are able to go into the conduction band pretty easily, and you don't really need to increase the temperature or force them to go there because they're readily available. They can go if they wish. How about a semiconductor? Well, if we take a look at a semiconductor, the band gap between the conduction band and the valence band is a lot smaller. And so it makes it possible for electrons in the valence band to jump up to go to the conduction band. And so this reasons are how you can move them. You need to give them some sort of energy. So thermal energy, high temperature, so any type of temperature movement, anything like that, you need to excite the bands so that, or excite, sorry, the electrons so that they can jump up into the band. And then now, if they are in the conduction band, this material can now conduct. And so that's what we call a semiconductor. Okay, so what does it mean when electrons are excited or to go into the excited states? Well, let's take a look at this schematic again, like from the previous picture, which takes a look at energy, and it takes a look at the states. So this would be the ground state. So this is the lowest possible position or configuration where electrons can sit, and they cannot go down any lower than the ground state. And so when these electrons are thermally agitated or excited or anything like that, they are able to go into the excited states. So let's take a look at carbon. So if we take a look at the ground state of carbon, carbon has 2 unpaired electrons in the 2p orbital region here. So because it's unpaired, that makes it a conduction electron, a conductive material. And carbon is a conductive material. It's not a good conductive material, but nonetheless it is a conductive material. And so if you were to excite the carbon, what can happen is one of the electrons, let's say from the 2s state, can jump up into the empty region here in the 2p orbital. And so you would have only two electrons that are paired, but 4 that are unpaired. And so we're going to exploit this fact when utilizing certain techniques in the lab as well. And I have this really nice picture over here I just wanted to show you. When you talk about, or when we're going to talk about X-ray emissions and things like that, I'd like for you to remember this picture so that you can see where it comes from. So again, here's our nucleus, and then our shells going in concentric circles around. So if I were to have some sort of radiation, it doesn't have to be X-ray, but let's say some sort of electromagnetic radiation coming in, and it's going to agitate or excite some of these electrons. So for example, an electron from this K shell, or the n equals 1 shell, it gets excited and it gets ejected. And so another one here in this state, so this was the so n equals 2 state, that also got ejected as well. Well, there's these new positions. It's like somebody leaving their house and it's empty, and so it's free for taking, right? So these electrons that are on the outside, so in the higher energy shells, they want to just jump in and get into those shells. So for example, another electron from an L state will jump into this state. But when it does that, we have energy emitted. So this comes out in the form of an X-ray. And so in this guy, for this guy that left, there's another electron in the M state that found an open position, and that one jumps in. And when it jumps into this position, an X-ray is emitted. So I'm just going to ask you to remember these as we talk later on about spectroscopy.
And the same thing happens with the LEDs, for example, right?
That's the idea, is that you're ejecting electrons, and so you have some sort of emission that occurs. It could be a photon, X-ray, depends on what the material is. Okay, so I do want to talk about crystal structure. So when you hear crystal, you probably think of an amethyst or some sort of rock or mineral. But in fact, the word crystal in solid state physics and material science is actually used to describe any solid. Okay? So it really has to do with the internal structure of the atoms. So the definition of a crystal is a solid with atoms ordered in a 3-dimensional periodic array known as a lattice. So probably when you think of a lattice, you think of a lattice fence or something like that. Okay. And so for a crystal, there's 2 types of crystals. One is a monocrystal, and we have polycrystal. So a monocrystal, this is otherwise known as a single crystal. So the reason why it's called a single crystal is because all the atoms in the material, they exhibit long-range order. So they're all ordered, and it's all continuous in a single direction. So they're very clean, very nice examples. If you're able to catch a single snowflake before it melts and put it under and analyze it, you'll see that in fact a snowflake is considered to be a single crystal because the orientation of the atomic planes inside are all in one direction. And what is applicable to electrical engineers, of course, with semiconductors is silicon. So when they create silicon wafers, they start off with a silicon boule. And the boule of silicon is actually grown to be a single crystal as well. And so what they do is they start off with just typical silicon. And silicon, really in its common form, is actually a polycrystal. But if you melt it down, there's certain techniques that they are able to grow it. So they melt it and then they end up pulling on it. When they pull on it, it forms this single crystal. So all the atomic structure inside is in one direction. And so all of the boules that they use in industry are manufactured from single crystals. Okay, so a polycrystal, so just like the name poly means more than one, this means that within these types of material, it contains many of these crystallites. And each of them is made up of different sizes and random orientation. So imagine the monocrystal, but a lot smaller. And they're all inside the material, and they're all shaped in different ways, in different directions, and they're all random inside. And so most materials are like this. So common metals, all of them are pretty much polycrystals. Many ceramics are found like that, rocks, and even ice cubes. So ice is also a polycrystal, even though snowflakes are single crystals. And then another definition, so crystal is when we have solids that are ordered inside, the atoms are ordered. An amorphous material is a solid that's non-crystalline, meaning that the material inside, so the atoms inside, is not ordered at a longer range. So here's some examples down here, some pictures. So crystalline would look like this, where all the atoms are nice and packed, and they're like this for the whole material. Polycrystalline, you can see that this bunch here is a small crystal, that one's a small crystal, that's a small crystal, and they look all random. They're all just sitting there. And then amorphous, it really has no real order, but it's still a solid. So an example of an amorphous material is glass, or polymers, and even gel. So I just want to show you here, this is a sample of a material that I made. This is nickel vanadium, so it's a ferromagnetic alloy. And if you look at it in the SEM, which we'll talk about in a little bit, you can actually see what's called grain boundaries. And so each of these regions here that you can imagine, okay, are these little guys here. And so these are the little crystallites within the material, and the dark areas are called grain boundaries. So another thing you wanted to know, or you should hear about at least, because when we do X-ray diffractometry, we would be interested in knowing information about the periodicity of the atoms. So we know that they can be ordered long range or at random, but how do you know? So some techniques you need to know a little bit more about the periodicity of the material. So a lattice is a three-dimensional array of positions in space. And this is where you would find atoms. So for example, I don't know if you guys can see this box here, but this would be what's called a lattice. And so the lattice, at the corner of each of the lattice, you have an atom that's sitting there. So that's the basic that's the basic idea behind the lattice. And then a unit cell. So they're a little bit different, but you might think of them sort of similar. A unit cell is the smallest unit of the crystal structure that repeats throughout. So here are some examples of unit cells. We won't go into we won't go into any detail about this actually. But just so that you know, I'll be showing you a material that has a cubic structure. And so the unit cell actually is repetitive throughout the material, and these are 7 categories of unit cells if you wanted to know about that. Okay, so materials. What are materials? Well, we use this all the time. We have them everywhere. And material classification. Well, these could be metals, ceramics, polymers, composites, of course, fuel and gas and liquid. But for purposes of material science and, of course, engineering, and the most commonly used, especially also for industry and things like that, are these 4 here. And so if we want to know, well, what does characterization mean? Well, in material science, various scientific techniques are used to observe and learn more about the physical and chemical properties of materials. So you're really investigating further into the material and what are the physical properties, what are the chemical properties, just to know more about the material. Of course, the type of technique that you utilize, it really depends upon the scale that you're observing. So how small are you looking, or how large are you looking? So you really need to know what it is you're looking for. So if we talk about structure scales, we start off with the very smallest scale, and this is subatomic, and this includes our elementary particles, electrons, protons, and neutrons. And here's a model of the protons and neutrons in the center of the nuclei there, and then 3 electrons orbiting around that. Does anyone know what material this is? Bonus points?
Carbon, lithium,
Close?
boron.
Beryllium. Be. Beryllium. Okay. So we have subatomic, we have atomic. Atomic means it's at a scale of atoms or molecules. So this combined would be considered an atom. And so the atom is considered to be the smallest particle of an element. And a little bit larger than that is a molecule. The molecule is made up of different kinds of atoms. And this is the smallest particle of a compound. So an example of a molecule maybe is a water molecule, which has 2 hydrogen and an oxygen, H2O. Okay, so we have subatomic, we have atomic, we have microscopic. So these are structures that are a little bit bigger than the atomic scale, but it's only visible with a microscope. And so a little bit larger than that would be macroscopic. And so this is something that you can see with your eyes, with no type of assistance from any type of tools or anything like that. So this is a really cool graph here. This is called the scale of things. And it takes a look at comparison of different sizes and scales. And I know it might be a little bit difficult to read, but you'll have your own individual one to look at in the PDF file. So I'd like for you to take a look at this scale here. At the very top, we start off with 1 centimeter. So if you might be about the width of some of your fingers. Mine, it's my thumb. Some of you might be your pinky. And so 1 centimeter is about right here. And if we go down in the scale, so 1 centimeter is equivalent of 10 millimeters, and then the next down is 1 millimeter. And so you're going to see that it's written in nanometers, because that's a very interesting unit to use when you're talking about microstructures. And so if we go down this spectrum here, there's the visible spectrum. And so this is when the size becomes, in terms of nanometers, about 1,000 nanometers. So red light wavelengths is about 700 nanometers. And so if we get smaller and smaller than that, we get down to about 0.1 micrometers. So a size of a human hair might be around right here. And if we go down even further, this is 0.01 micrometers, and then a nanometer. And of course, all the way at the bottom, this is 0.1 nanometers. Another unit that is quite utilized frequently in material science is an angstrom. So this is 10 to the minus 10 meters. And structures, or atomic structures, are denoted with this unit. So just to give you an idea, an ant would be about right here somewhere. Red blood cells is approximately in this region, and silicon atoms would be around right here. So those are all natural items or natural things. Here are all man-made stuff. So this is a pinhead, and then if we take a look at what else here? So here's some MEMS devices, and so here's some carbon nanotubes. So those are all very small structures. Okay, so the type of technique that you'd want to utilize depends on the scale you're looking for. So macroscopic, of course, you look at something with your eye, if it looks shiny, if it's rough, or whatever the case may be. Microscopic, you need to use some sort of microscopic tool. And so you have different techniques also. So out of these two categories, what do you utilize? Well, there's different techniques to investigate further. So we have diffraction techniques, spectroscopic techniques, optical, electrical and magnetic, and thermal techniques. And investigating the properties using this techniques gives us some sort of insight into the microstructure, the composition, the crystal structure, and the bonding of a material. So then we come to our neighbor next door here, so the Keck laboratory. So it's called the Keck Microanalysis Laboratory. Why is it called Microanalysis Laboratory? It's because observing and analyzing behavior, we're in a very small region in a material. So some of the items that I mentioned previously for techniques are not all utilized in the Keck laboratory, so I only listed the ones that we do have. So for optical microscopy, we have the optical microscope, which is what anybody can use, maybe in biology or whatnot. We have the confocal scanning fluorescence imaging system. For electron microscopy, we have the scanning electron microscope, the atomic force microscope. And for spectroscopic techniques, we have the EDX, or the energy dispersive X-ray, the Auger electron, the laser-induced breakdown, and the Fourier transform infrared. And so for diffraction techniques, which is also considered in a way part of spectroscopic, we have X-ray diffraction. So this is using different energy wavelengths to investigate materials. So I'm just starting with the microscope just to give you a general overview to get into the other materials. Most microscopes are compound microscopes, so it uses a series of lenses to function. So usually you have lenses that you look into, and lenses from the bottom that you can control the magnification. And the range can go anywhere up to 1,000 times. But it's also limited. So we use visible light to use a microscope. And the wavelength of light is anywhere between 400 to 700 nanometers. So 400 nanometers being blue and 700 nanometers being red. And the smallest size that you can actually see would be half the smallest wavelength. So since the smallest wavelength of light is 400 nanometers, half of that is 200 nanometers. This is the smallest scale that you can actually visibly see. And so we are limited if we want to view structures smaller than 200 nanometers. So in that case, that's why we need to use the electron microscope. So I just want to show you a comparison of nanofibers. This is using a regular optical microscope, and this is using a SEM. So you could definitely see there's a huge difference between the two, and a lot of detail that you're getting with the SEM that you're not seeing at all with the microscope, the optical microscope. So, scanning electron microscope. So this uses a beam of highly energetic electrons. So this is from 10 to 20 kiloelectron volts. And of course, we use this to examine objects on a very small scale. So here is an idea of what it looks like. This is a schematic diagram. We have an electron gun that creates a beam of electrons that gets emitted from here. There is an anode or an accelerator. So this is a negatively charged region here. And so since electrons are negatively charged and the anode is negatively charged, it accelerates the electrons. And so when it accelerates the electrons, they're traveling pretty fast, but you need to control them. And so that's why there's these magnetic lenses to help focus the beam. And so the beam actually gets focused onto the sample, and the beam actually gets scanned across the sample, just like its name, scanning electron microscope. And so when it scans across the sample, it's going to hit the electrons that are in the material, and the electrons end up scattering. So how much scattering and the number that's detected at the detectors gives us a few bits of information. First, it gives us information about the sample height. It gives us some information about the sample chemistry and the crystal structure. So along with the electrons getting scattered, we also are producing X-rays. And so if you analyze the X-rays, you can see what elements that exist in the sample. And this is the energy dispersive X-ray, which I will be talking about afterwards. But these two are actually embedded in the same device. So the SEM would be this portion, the EDX would be this portion here. So two different techniques. So if we take a look at what the SEM does, it actually takes really nice pictures. Okay, so this is a material that I created as a graduate student. This is nickel vanadium, so ferromagnetic nickel, and you dilute it with vanadium. And the idea was to do magnetic measurements because I was interested in knowing the magnetism of the material. But nonetheless, this is the sample that I created. I used an arc melt method, so basically I cut up specific concentrations of the material, melted them together, and created this really nice shiny sample here. And then I also annealed the sample, which means I baked it in the oven for a little bit. But when I change the concentration, so X is denoted as concentration of vanadium. If I change the concentration of vanadium, you can actually, there's some applications that you can utilize with this, and it's been known in the past to be used for magnetic recording, so for magnetic recording tapes. So it has some pretty interesting properties, but the purpose for today, I really just wanted to show you the pictures on the SEM that I used. So if this is a specific concentration, it's not the same one in this sample here in the SEM, but this is a picture of another vanadium concentration. And this sample was sent to me after I graduated, so somebody else had made this. But when I looked at the material, so if you take a look at the sample, it's pretty tiny, it's about 4 millimeters, so it's really, really small. And there was something like little pokey sticking out on the side of the sample. And so it was interesting to see, okay, well, what is this material? Did it not get blended very well when it was arc melted? What happened to it? Why is there some junk on the outside? Well, taking a look at this a little bit further, this is what I saw. So really beautiful picture of ups and downs and craters and things like that. And so this is magnified, let's see, so this is magnified at 800 times. This is magnified at 40 times. So it's much larger than the scale here. This little tiny box here is approximately to scale. So just to give you an idea of the size of this picture here. So I had it in the electron microscope, and then I also did some energy dispersive X-ray measurements on it, and you'll see later on what the results were. But I found out that it was another material stuck on there. And so what it turned out to be was tantalum. And the reason why it was tantalum, and I knew why exactly, because one of the things that is done when you anneal the sample or bake it is that you have to, what we did was we put it under a vacuum. So it was sealed in a quartz tube, but it was wrapped in tantalum, because tantalum actually absorbs oxygen, and I didn't want the samples to get oxidized. So any remaining oxygen would have been absorbed by the tantalum, but it looks as if some of the tantalum got melted and actually was sitting on the surface, on the outside surface of this material. So, anyways, so going on to microscopic techniques, so here I want to mention a scanning probe microscope. So we actually have, so let me just explain. This is a broad category. Several techniques are actually grouped under this name, and they are the atomic force microscope, the scanning tunneling microscope, and the near field scanning optical microscope. So all three of them utilize basically the same idea. You're going to image and measure surfaces on a small scale. You utilize an extremely sharp tip. And so the radius of curvature on this tip is from 3 to 50 nanometers, so it's very tiny. And the tip is mounted on a flexible cantilever, which is scanned across the sample surface. I'm going to show you a picture afterwards. But the idea behind all three of these is that when the tip moves in the vicinity of the object, the interaction forces is what gives us the information about the surface of the material. So we're only going to take a look at the atomic force microscope. And this is the atomic force microscope right here. So it looks just like a regular microscope, except it's actually embedded inside of this device with a cover, because there's actually a laser that's inside of it. And a very tiny region right underneath this table. So this is a retractable table. It moves in the X, Y, and Z directions. This is the cantilever. So this is the actual, this is called the cantilever chip. And this line is the cantilever. And you really can't see it because the resolution is bad here, but it looks better on the slides. Down here, which you cannot see at all, is the actual tip. And so if you see an SEM picture of that, here's the cantilever, which is this white thing here, and at the very end of it, there's this sharp tip. And so the scale of this is 5 micrometers. So the atomic force microscope, this is used for imaging, measuring, and manipulating matter at the nanoscale. So you can take 3D images of your sample. So this sharp tip here, this is what's used to probe the surface. And it does that using the idea that there's interaction forces between this tip and the surface of your material. So this is the cantilever here, which is this arm, and the little tip. And the tip actually goes across the surface. And I don't know if you can see this very well, but the atoms that are in the tip are very close to the atoms in the surface of the material. And so there's an interaction force that is exerted at that point between them. And so this is what helps to give information about the material itself. I have some really nice pictures to show you, because this is the best way really to see how things are. So this is the nickel vanadium alloy one more time. And so I was just interested to take a look at what it looked like underneath the surface. So after spending so many years working with the material, I feel kind of a close bond with it, you know what I mean? Anyway, so the scale of this, just to give you an idea, this is about 40 micrometers, or micrometers is also called microns. The scale of this is a little bit smaller. This is about 10 microns across. So about this big is what you see here. And then this is about 2 microns across. So the atomic force microscope is really nice for taking a really deep look into a sample. So especially if you want to take a look at semiconducting materials, if you're making thin films or anything like that, it's good to see the characteristics of the material itself. So you can take this image, this is a 2D image, but you can also take a look at the 3-dimensional image of this. And what's nice about taking a look at the 3-dimensional image is that you can definitely see that there's some discrepancies. There's some pits here, there's some like little mounds. And so these are all characteristics of a material that you might be interested in finding out. So you can even do measurements with the AFM. So you can actually scan across and do a line analysis, and this will give you a graph to show you the actual quantities of the material. So for example, this dip here looks to me the lowest point of the sample in this screen, and this is what is used as the 0 mark, and the highest point is approximately going to be about, I don't know, roughly 1,000-ish. 1,000 nanometers. So that's the highest point. So that's about the thickness of the surface here. Yes?
So why are the pits or the holes significant to the material?
Well, this material is a polycrystal. So this could be like a grain boundary, where the two areas actually meet. So for this sample, it's not really that significant because I know it's a polycrystal, but this type of measurements would be interesting for other types of materials, semiconductors, or where the scale really matters in that case. Question?
Since you're like dragging the thing across the sample, can you only measure like something that's solid rather than like a liquid or something?
That's a good question. You can actually use any type of material in the atomic force microscope because it's taking, yeah, so you could do it, but you would probably have to take a look at the thickness or things like that. So it's better if you have something that's a flat surface just because the way it's actually positioned in the microscope and the cantilever only, you have to be careful not to smash the cantilever or the tip or else it breaks and it doesn't work. So you have to, if you're working with other types of surfaces, you have to be careful. Okay. Okay. So this is the other type of, actually I probably didn't have it in the original slide, but this is another microscopic technique that you would utilize. So similar again to a microscope, an optical microscope. This is the confocal scanning laser imaging. So here's a picture of this. This one is actually not in the lab right next door, but in that other secret door on the other side of the lab. And so this guy, what this is for is to generate high resolution, high contrast 3D imaging. And this is more utilized for biological materials, but of course you can put any type of sample in there. The idea behind this is that you utilize a laser. And so you utilize a laser that's where the beam is focused in a specific spot. So here's your laser source. You have what's called these apertures. So aperture is an opening. So your eye opening is called as an aperture as well. And so if you make the aperture really small, you actually focus the beam. And so eventually when you hit the sample, I don't know where the sample is on here. I think it's like right here somewhere. Anyways, you're basically, when you use these apertures, you're getting rid of any stray light rays. So light, when it comes down, it goes in all directions. And so you get some scattering and you get things that bounce, and it actually can cause some aberrations in your images. And you don't really want that. And so the idea is you utilize this to focus the beam to give you some really nice pictures. So something called fluorescence. So fluorescence and transmitted light is detected from the sample. Fluorescence is low energy emission of light. So when an atom, when a material is bombarded with high energy radiation, there's a lower energy emission that's emitted, and this is the fluorescence. So I know all of you have utilized fluorescence at some point or have interacted with fluorescence. For any of you who have used a highlighter, this is an example of fluorescence because there are fluorescent materials, molecules inside the liquid of the ink, so that when you write on your paper, the light that gets reflected off of it shows it as much brighter. And so that's the idea behind fluorescence. So you see something that's really bright. So basically, this whole expensive device that's very sensitive is just a big highlighter pen, right? Okay.
So this is almost like an interferometer, and then if you're using, in fact, a laser, it's going to be monochromatic. So here, then, on that page, I mean, on the far end, basically, you would be having, you should be seeing some of the interference and so on, right? Circles or whatever, or not?
So the idea is that you could, but the idea behind the confocal, there's a confocal lens that's, when it's inserted, it actually narrows the beam so it gets rid of any type of interference or anything like that. So the only beam that you're utilizing, that you're seeing, is the beam that's being focused. So it's directly straight on the sample.
No, I'm talking the interference of the two beams, one from the horizontal, the other vertical, which go there at the end on the screen at the far end, are going to interfere.
Well,
you're going to have circles.
Yeah, I see what you're saying. The idea is that this scans back and forth, so when it looks like it's interfering, it's actually because there's movement going on. So the whole idea is that it's scanning the surface of the material, and so what you actually see is a very nice image. And I'll show you right now, actually. Very, very beautiful images that come from this. So, so just to give you a comparison, these are 3 biological objects. These are viewed in a typical microscope. Of course, optical is very small scale. But as you can see, the definition is really not there. This is when you utilize the confocal scanning feature of it. So you can see all the little details and all these grooves that you would not normally see in a typical image. So here, this is where you get a lot of light scattering. And so the light scattering actually dilutes the picture, so you don't see the details. So when you use the confocal apertures, you get rid of the interference, and so you're able to see a very clear image. So if you were interested in knowing what these are, this is some sort of animal tissue or medulla. This is a rabbit tendon, a part of the muscle. And this is a sunflower seed pollen. So it's interesting. I was pretty interested to see that because it looks like a sunflower itself. So applications to utilize this. So it's definitely used in the biological field. So all the departments in our school, we have many disciplines. So biology utilizes this as well. But this is also very good to find cracks or defects in a material. So if you had some sort of semiconducting material or a thin film that you want to take a look at, you would be able to use this device to see any cracks or anything inside the material if you're trying to get a pure sample or something that didn't have any defects in there. So this would be good for that type of application. Any questions about this? Yeah.
Question. In that case, would you use the fluorescence factor?
Yes, you would definitely use yes, you would use the fluorescence factor for the cracks and the defects. That's what helps to highlight them, so to speak. So you see how the images are really bright. Of course, they're not this color, but the fluorescence is used to magnify and to give a different energy scale that looks. So yeah, definitely would be able to use that. Okay, so far I've talked about microscopic measurements. Now I'm starting to talk about spectroscopic measurements. So going back to the picture that I showed you guys about the energy getting emitted when you have electrons getting kicked out and then energy spectras created after that. So now this is when we're going to start looking into that. So this is the energy dispersive X-ray. It's attached to the SEM. And so X-rays are actually produced by energetic electrons. So it's the same energy scale as the SEM, so between 10 to 20 kiloelectron volts. And so these X-rays hit atoms into the sample. And so the analysis of what's picked up at the detector will actually show you what type of elements are in that material. So the electrons that are being scattered, when you hit the atoms, all the atoms in every type of material is very different, right? So the sizes of the atoms, the spacing of the atoms, and things like that. And so the EDX is able to determine what types of quantities are in a material. So here's my nickel vanadium sample that I showed you guys. And you will see that there are peaks. So these are what the spectra, these are called the spectra peaks, and you're really not able to see this guy here, but this gives me the percentage of the component that's in the sample. So for example, I was making an alloy with a specific concentration. So if I wanted to test how good my method was, I would put it into this device and I would be able to verify, is it indeed that concentration or not? And so this sample actually has, guess what? A little bit of tantalum in there. And so the method, while it's very good for a bulk measurement, the technique for annealing probably would not work if I was to try to do something that was a little bit more sensitive to the material or the composition. So this could be operated at room temperature or at liquid nitrogen temperature as well. So this is this is the type of spectra that you'd be able to get from that. Oh, what I did want to say, the detectors, when they count the emission that's coming in, so what they're picking up on, so this is the number of counts that they're getting. So the more counts they get, the higher the peaks are. So that's basically what I wanted to mention on that. Okay.
I have a question.
Yeah.
What I What I haven't realized, or the reason why for cooling. What is the reason behind the cooling and need for the...
For low temperature type cooling? Why? Okay, well let's talk about the atomic electronic structure of materials. So what happens when atoms or just any material is at room temperature or it gets heated? What happens? The electrons are just bouncing everywhere. So you're not able to get a real, a true fundamental behavior from these materials. So the idea is to trap them. How do you do that? You cool them down. So any of you, if you're cold, if you're out there, it's a cold day, you don't have a jacket, how do you feel? Like you don't want to move, right? You're frigid like this, you don't want to move. You just want to sit in front of a fireplace and drink hot chocolate or something, right? So the same idea, when you take a material and put it under such a low temperature environment, you're actually bringing down the energy state of the material. And so you're causing the electrons not to be bouncing around, but this gives you a better idea of how the material really operates without extra interference. Okay. Okay. So this is the Auger spectrometer, and I don't know if I'm saying it correctly or not. So the idea behind this one, this also is an X-ray type of spectrometer. So here's a little schematic diagram. So you have some electrons coming in, some high energy electrons from a source. These are what's called the primary electrons coming in. And so it hits a sample, the surface of a sample, and you get all these types of emissions that are kicked out. So you have secondary electrons, so the primary come in, secondary go out. You have these Auger electrons, you have characteristic X-rays, you might have photons, and backscattered electrons. Now, of course, this technique is just taking a look at this type of electron, whereas maybe the EDX we'll take a look at the secondary electrons. So this is also a surface type of technique. This is utilizing the emission of lower energy electrons. So these are between 2 kiloelectron volts and 10 kiloelectron volts, whereas the EDX was a little bit higher than that. And so the idea behind this spectrometer is based upon the kinetic energy of the emitted electrons. So how fast these are actually going to be traveling, or how much energy they have. So different kinetic energy will result from different types of samples. So different elements will give you different types of structures. So you're able to determine what's inside of a sample based upon knowing what the kinetic energy of the material is. So this is used to determine quantitative composition analysis of the surface layer of a sample and how clean your sample is. So if you're taking a look at semiconductor and you want to look at the impurities when you're doping the semiconductor, this is what's utilized for taking a look at that. So here is a graph of the results. So it takes a look, of course, at the signal, the strength, and it takes a look at the kinetic energy with units of electron volts. And we see that the spectra has 3 peaks, so 1, 2, and then the major one is here. And so the characteristic of this peak is exclusively just for palladium. And so that's how you would be able to analyze what's in your material. Based upon the peaks that are found from this spectra. Yes?
I remember when we toured the Keck lab, it told us one of the techniques was like, I don't know how to, it like destroyed the sample when you...
We're going to talk about that.
Is that
No, this is not. So you don't actually destroy the sample. So when I say that the electrons are emitted, of course they're still within. They don't get ejected out into space or anything like that, right? So they're still contained within the sample. But we're thinking of the libs. So I am going to be talking about that.
Oh, okay.
Yeah.
I just jumped ahead a little.
Yeah, no, that's cool. I'm glad you remembered that. All right. Any questions about this one? Okay, there you go. This is what you were talking about. So LIBS, otherwise known as the laser-induced breakdown spectroscopy. So just like the name, it has the word breakdown in there. And so this, you automatically think, okay, well, it's doing something to damage the sample, and actually it does damage the sample. So this is the actual device. It's very small, but it's actually very destructive for a material. But the whole purpose of it, it's a rapid chemical analysis technique, and it uses short laser pulses, so very rapid short laser pulses, and it creates a plasma on top of the surface of a material. And so you're actually damaging the surface of the sample while you're doing that, and that's what we called ablation or laser ablation. So this is when you damage a material or where the laser damages the surface of a certain material. So the high energy pulse, or sorry, the short laser pulses are actually hitting the surface of a sample, it's breaking it down, and you're actually creating a plasma. And so a plasma is just a charged region, so a charged gas. So you're having a bunch of charges, very high temperatures. I mean, they've been observed to have the temperatures as high as 30,000 Kelvin, which is a very extremely high temperature. So anyways, so when the pulses are hitting the surface and it's creating this ablation, eventually you turn off the laser pulses, and so the plasma starts to cool off. So again, thinking back to our energy states, you're exciting all these electrons and they're getting to these high energy states, and when you turn off the source of the agitation, they start to go back into their ground states, or where they want to sit down. And so when you do that, you're causing light to be emitted by the plasma, and there's these discrete spectra peaks that's very exclusive to specific material, again, because each material has specific atom sizes, atom spacing, and things like that. And so here, this is an example of a material. So this actually has a bunch of different peaks. So here is a silicon. So in the red, you see silicon, and then the blue is germanium. And so each of these, so for the red ones, these are all characteristic peaks of silicon, and the blue are characteristic peaks of germanium. And so those are both found in this material. So it's probably some sort of semiconducting material, in fact. Unfortunately, this does damage the sample, so if you wanted to reuse your sample, you might not be able to do that. Any questions on this? Yes?
If you're creating a high temperature, is there a background of black body radiation that gets subtracted away?
I believe that the spectrometer already deals with all of that. So what you're seeing here is purely the results of the material itself and not any type of background. So, okay. So another spectroscopic technique, this is Fourier transform infrared. So a lot of you have seen Fourier transform in your math classes or some sort of class, and infrared, we know this as being a specific electromagnetic radiation. Of course, you associate this with heat from the sun or any type of heat. This would be infrared. So if we take a look at the electromagnetic spectrum here, all the way on the left-hand side, these are very high frequency energy. This is gamma rays, and then X-rays, ultraviolet. And then we have our visible spectrum of our rainbows, our rainbow colors, and then we have infrared. So this is always going to be right next to the red portion on the visible spectrum, and that's how you can remember where it is positioned. And if you take the infrared spectrum and then open it up a little bit, just to take a deeper look inside, there are three regions. There's near infrared, mid-infrared, and far infrared. And so the different techniques, there's different spectrometers that would be in maybe each one of these regions, or maybe would utilize one or the other, but they're all for different applications. So this specific one that we have is in the mid-infrared range, and this takes a look at vibrations of molecules. And so the Fourier transform infrared actually takes a look at the vibrations of the atoms, and that's what it's utilized for. So this technique is used to measure absorption or emission spectra of any type of a solid, liquid, or a gas. It collects data over the infrared spectrum simultaneously. So meaning that it's not just scanning over a specific region, it does the measurement all at one time. And then it uses Fourier transform to convert the data into the spectrum. So this is a very reliable method, very sensitive method, used to identify any unknown materials, used to look at the quality or consistency of a sample and the amount of components in a mixture. So if I was to take a look at the results of it, here is a graph of absorbance. So this is this specific method looks at the absorbance, because you can look at that or the transmission. So emission, excuse me. So here's the absorbance versus what's called wave number. So wave number is actually defined as 1 divided by the wavelength. So I took a little picture of the infrared spectrum from the previous page, and it gives you the wavelength of each of the spectra portions here. So at the closer to the red portion of the near infrared, this is 1 micrometer. So that's the wavelength of that wave, is 1 micrometer. And it goes to 5 micrometers, 30 micrometers, and 200 micrometers. So we can see that the wavelength is actually increasing as we go towards the right, which means that the frequency is decreasing because they're inverse. But the wave number in each of these regions, and the reason why I put it up here is so you can see what range this material or this device was taking a look at. And so since this is between 4,000 and 1,000 inverse centimeters, this is taking a look at maybe this region here. So this device, I got this off of the internet, the device that was taking this spectra was utilized in the near infrared and the mid infrared. So our device only takes a look at the mid infrared. And so the peaks actually determine what type of material is in the sample. And of course, the size of the peak gives you an indication of how much of that material is inside here. So this is really utilized for many things. You can definitely use it for semiconductors to measure quantity of the material that you're creating or that you have. It's used in manufacturing for quality control or quality assurance applications. It's used in food manufacturers to make sure that they don't have, pieces of glass in the food or any type of junk or any type of contaminants before they sell food to people. It's used in forensic analysis, and it's also used to measure blood alcohol levels. So if somebody gets stopped by the police, they actually have one of these Fourier transform infrared spectrometers. They're really tiny. They're just like about the size of a phone. And you breathe right into it, and all the instrumentation analyzes your breath and can determine the alcohol level instantly on the spot. So anyways, some very interesting applications for this technique. So we also have X-ray diffraction in our lab. So this is the X-ray diffractometer. What's interesting about this, it's used for many different applications. So the idea is that you have an X-ray beam that hits a sample, and the X-ray beam is at an angle theta with the sample surface. And so there's a detector that's picking up all the scattered scans here. And so this detector is at 2 theta from the surface or from the line of the original beam. So it's used to identify unknown crystalline materials. So if you had a sample and you didn't know what it was, you could also utilize it in an X-ray diffractometer. So you can actually determine what the crystal structure is. So if you had a really unknown material, didn't know what it was, you could take a look at what the crystal structure is. You can take a look at how pure that is, because of course you're taking a look at the what's inside of it. You can take a look at the phase composition of that material, and also lattice parameters. So again, this is information about the crystal structure of the material. It describes the unit cell in a material. And so the lattice parameters were really going to be dependent upon other things, so such as alloying. So if you're alloying a material, that's going to change the lattice parameters. If you're doping a semiconductor, and other types of parameters as well. And you can actually look at strain at the macro scale and at the micro scale. You can characterize thin films, so thickness, density, and things like that. So here's this is an example of table salt. So this is the atomic structure of sodium chloride. Okay, so our device next door is actually a powder X-ray diffractometer, which means that you have to take your material and grind it into a powder. And so why do you do this? Well, especially if you're using a polycrystalline material, you have random orientation all over the place. This helps to have a more let's say, a smooth signal. So it helps the signal a little bit better here. So the idea is that you have these X-rays coming in, and they hit the atoms that are on this lattice here. And so, of course, they're going to bounce off. And so if you take a look at, so there's two things I want to mention. First is that all the atoms are on a specific plane, so they're all spaced a specific distance d away from each other. And other thing that you look at is how in sync are the waves. So if the waves are in sync with each other, this is what's called constructive interference. And if the waves are out of sync with each other, they actually cancel each other out, and this is destructive interference. So this uses the constructive interference of these of the scattering process, and what you're end up going to see is very sharp peaks at where this has the constructive interference. And so this gives us an idea about the crystal structure using this formula. This is Bragg's formula. This is utilizing the wavelength of the X-rays, and you're able to find out the atomic spacing of the material through this. So you're able to find out your lattice constants just based upon the X-ray diffraction. So this is what you would see. So you have peaks, but you're going to see that these have all these funny numbers. So 111, 200, and all these things. Well, these identify the planes in a material. And I won't get into too much detail about this, but this is more solid state physics. But the idea is that for a specific material, you're going to have distinguished peaks. So these peaks are actually a result of nickel, because this is the dominant, so I use this for my nickel vanadium sample. So how much vanadium did I put? Very little. So this is about maybe 12%, 13% vanadium. So it's not very much. So it's still predominantly nickel here. So this gives you an idea of what is in the material. These peaks would give you an idea of the crystal structure. And so this little picture here takes a look at, let's see, I think it was this one. So the 200 peak would be this. If I were to blow this up, I can see that different samples are not exactly on top of each other. And this gives me an indication of the lattice constant, which is here. So what this graph is saying is that this is pure nickel, and if I add more vanadium to it, so if I'm diluting the alloy, I'm increasing the lattice constant, and so this is an indication of the crystal structure of the material. Okay. Oh, I'm sorry, I went really over here. Okay. Okay, so we do have a sputter deposition system. This is a very small device. This is only really used because of our SEM. The idea is that you have a sputtering gas coming in. We usually use argon. This hits the surface of your sputtering target. So this can be gold, this can be whatever material you like. And atoms are ejected. And so when they're ejected, they coat a substrate. And so you're actually creating a thin film material using this. So again, the sputtering device that we have in the lab next door, it was originally used for utilizing the SEM, especially if you don't have a conductive material in the SEM and you want to coat it with a thin conductive layer so you're able to take pictures and things like that. But it is functional. You can still coat up to, I think, 300 angstrom or 30 nanometers if you wish to do so. And I think pretty much I'm done. This is just something I threw in because this is a very quick technique to measure resistivity. So this is an electrical measurement, the 4-probe method. So this is, again, a very nickel vanadium sample. The distance here is about 1 millimeter, so you can imagine how tiny this is. And you had to coat these all by hand using silver epoxy. And the idea is that you're able to get the electrical conductivity of a material this way. Okay, anyways. I think I didn't realize I've gone over so much.
Class at 6 o'clock.
Yeah, no worries. I'm sorry. I was having so much fun, so I didn't realize the time.
Yeah.
Okay, so anyways, all of you will have these slides. I really wanted to mention that companies are very interested in these type of techniques. So if you are able to utilize or learn any of these, especially if you go into a company in the semiconductor industry, so Apple, SanDisk, Intel, and so forth, they look for people who know how to do device characterization, so which utilize a lot of these techniques, or failure analysis to see how a good quality your sample is. And it's also used to investigate some issues. So again, one of the impending issues that's we're facing is what do we do when our transistor size gets smaller, right? So, or that we reach our limitation. So the integrated circuits that we're using, our integrated circuits are roughly 5 billion transistors that are about 14 nanometers in size, but we're approaching a limitation. So around 5 nanometers is what's projected in the year 2020, and then after that, we can't utilize anything. So, or we won't be able to utilize these to go any smaller. So I was just taking a look at some solutions. So maybe you guys can take a look at this, add to it, see what's out there. And also, has anybody heard about three-dimensional NANDs?
Yes.
So this is new. I guess this was out. I read it in the Electrical Engineering Times. This is an alternative way. Instead of going smaller in transistor size, this is just going in a larger scale, three-dimensional.
3D transistor, right?
3D transistor.
Yeah.
So anyways, I thought this was interesting. I thought to mention it. These can all be characterized using the tools in the lab next door. Thank you so much for your time. I'm sorry that I went over, but it was a pleasure.